Hello and welcome to my YouTube channel. I'm going to continue to solve the last year Applied Electronics examination questions. I already solved the first 25 multiple choice questions. I'm going to continue with the next 25. So starting from question 26. So question 26, we have a transistor has a collector current of 10 millivolts. So meaning I have my IC is equals to 10 raised to power minus 3 amps. Then if the gain is what? 120. So the gain here is beta DC, which is 120. And we know that for the beta DC is going to be equal to what? Mean the output current, mean the collector current over 1. The base current. So you can see here we have to find what is the base current. So we just make the base current the subject, and with this we are going to get base current will be equals to beta DC equals to meaning collector current over beta DC. So we're just going to do it straightforward. So that will just be 10 milli. So I will have 10 divided by 120. That gives me 0.83. We get 0.083 milli, 10 raised to power minus 3. So we change this to what? Micro. So it will be what? 1, 2, 3. So I have 83. So we get the answer here to be B. Now moving to the next question. A transistor is connected in common emitter configuration. Common emitter configuration. The collector supply is 8 volts, and then the voltage drop across a resistor of 800 ohms in the collector circuit is 0.8 volts. If the current gain alpha DC is 0.96, find the base current. So with this one, you can see alpha DC, we know it's going to equal output current over what the emitter current. But here you can see we have to find the base current, right? And at the same time, we know emitter current is going to be equal to 1. Base current plus collector current, right? So IB plus IC. So we try and get all this. So so from this that we have done so far, you can see that from the question, we are giving the voltage drop, right, across 800 ohms. So that voltage across the 800 ohms is going to be the voltage across the load, right, which is VC will be equals to IC times RC. So we make IC here the subject, then we get here to be voltage, which is 0.8 divided by 800. That is going to give us 0.8 divided by 800. That is going to have 1 milli. 1 milli amps. And we have 1 milliamps. Then from there, we can now try and get what our IE, right? Because we can make from here, if I make the base current the subject, I get IE minus IC. So now we know IC. Let's try and get IE. And from this, the alpha DC we know that the emitter current will be equals to IC over the alpha DC. So I get here to be, we are going to now get, meaning 1 milli over 0.96. So we have divide this by 0.96. So we are going to get here to be 1.042 milli, right? Milliamps. So we get there. Now that we have, now just do the subtraction, right? So I can now take this one minus, that is 1 milli, meaning 1 times 10 raised power minus 3. So we get here to be so the answer become for IB. Okay, this is IB. Is going to be close to 4 point, let's say 1, 2, or 4.2. Let's make it 4 point. Because we have here is 4.16, right? Times 10 power minus 5. So you can see the possible answers that we have then in micro. So that is just going to 4.1 F 41.16 micro. And from there you can see that that is going to be what? C, right? We have this one to be C. Sorry, to be D. Okay. This becomes D. Okay. Now question 28. In a common base connection, the emitter current is 1 milli. If the emitter current is open, the collector current is what? 0. Is 40 microamps. Find the total current given that alpha DC is close to 0.92. So to get this, the total collector current. So total collector current here is going to be close to the what? The initial collector current plus the what? The collector current. So first, you can see the initial collector current is what? 40 microamps. So this one is 40 micro. So now we have to find the what? IC, right? The collector current. Now that's due to the what? The emitter current being 1 milli. So to get that, again, we come and write the formula, which is alpha DC is equals to what? Collector current over emitter current. And this becomes IC becomes which is alpha here, this is 0.92 times emitter current being 1 milli. So this is going to give us, I'll get IC to be equals to, that'll just be 0.92 times 10 to the power minus 3 amps. So we get this here. Now that we have them, we just come and add it so that we get the total. So we add it here plus 0.92 times 10 to the power minus 3. And what do we get? Or if we add this, so one way you can go about doing it by maybe making this one to also be in terms of micro. So I can have 40 10 to the power minus 6 plus this one in terms of micro, well, 920, right? Times 10 to the power minus 3. Okay, minus 6 rather. So that I can have 40 plus 920 is going to be 960 micro amps. So when you come here, you can see that we don't have micro. We have in terms of milli. So, and this is going to what? 0.96. So the answer here become B. 96 milli amps. Moving forward to question 29. Find alpha DC rating of the transistor shown in figure 1. Hence, determine the value of what? The collector current. Okay. So we have to find IC. So this one is repeated past question. So I'm not going to solve this one. When you go and look at the lesson I solved earlier, so the answer here will be D. Which of the following is not an example of transistor? So here we have here it become SCR. It's not a transistor. Question 31. In a bipolar junction transistor, the flow of current is taken in the direction opposite to the flow of current is taken in a direction opposite to the flow of electrons, right? So here we look at the direction opposite the two, but when it comes to direction into the flow of current, that indicates there were people. So it's taking the direction opposite to the flow of electron here. All the following are example application of Thyristor, except here again this repeated question we have the answer is 32. Now you look at this question, preamble 1, question 33 to 35 refer to the silicon transistor circuit shown in figure 2. So we have figure 2 here. Now so with this, the first question 33, the value of the emitter current IE is, so IE, we know IE is going to be equals to base current plus what? The collector current. So let's try and get these two parameters. So base current, based on this, to get the base current, which is here, IB. So we come to this loop, we consider as loop 1. We apply Kirchhoff voltage law to loop 1. And we get here to be, we can do it straightforward. So we are moving, let's say we are moving clockwise. So I have 5 minus, here is going to what? The voltage across this. That will be what? IB times the resistance there, which is 10 kilo. Right? Then minus, here we have what we refer to as what? VBE. So which is usually for since this is silicon, is going to be 0.7, is equals to 0. So the base current becomes 5 minus 0.7 over 10 raised to the power 3. So if this 5 minus 0.7, we get 4.3. Then we divide this say by 10. That gives us 0.43. We bring this, the 10 raised to the power 3 up, it becomes milli. 10 raised to the power minus 3. So we have this for IV. Now let's get IC. To get IC, we are giving here beta DC. And we know beta DC is equals to what? Collector current over what? The base current. Now I can get IC, which is 150 times 0.43 times 10 to the power minus 3. So that just this times 150. So I'm going to get 64.5 times 10 to the power minus 3 times. Now that we have done this, we can just come and add this current up. Then we get what? IB. So when we do that, we are going to get the answer to be 64.9 milliamps. So you do the addition. The value of VCE. When it comes to VCE, again, to get this, VCE is here. This is our VCE. Or to get the VCE, we are going to what? Apply Kirchhoff voltage law to this loop. We can call this loop 2. So we have our loop 2 here. In the applying this, you can see here we have VCC, I have 10. So this is a resistor. So there's going to be a voltage drop. So the voltage there is going to be the current which is passing. We call it IC. I have my IC. And IC, we know IC to be what? 64.5. That's 10 power minus 3. Then times the resistance there, which is 100. Then minus VCE will give us 0. So we make VCE the subject. That means we calculate this and we send this. Now that we have done this, so I'll just take 10 minus bracket 64.5 times 10 to the power minus 3. And then what do we get? No, times here for what to bring here. We have times 100 here. Okay, let me do this. So here, by looking, even if we just do that, it will just be 10 minus. Okay, let me simplify this. 64.5 times 10 raised to the power minus. We can even just see, right? This 10 raised to the power, this is 100. That's 10 raised to the power 2. So if you add this, you get here to be now 10 raised to the power minus 1. So this just becomes 6.45. So 10 minus 6.45 get 3.55. So the answer here is D. Now that we've gotten VCE, question 35, the value of VCB. VCB, this is our VCB, is here. So to get VCB, the sum of what VCB and VB will give us VCE. So I can write VCE will be equals to sum of VCB plus VBE. So VCB here becomes, we know VCE to be what? 3.55, then minus 0.75. 0.7. So we have 3.55 minus 0.7. We get here to be. So the answer here is 2.85. So the answer here is 2.8. Moving forward to question 36. A silicon control rectifier is a bidirectional switch. Silicon control rectifier is bidirectional switch. So this is going to be false. So we have this is one direction. It's just similar to a diode, right? So we have one direction. We have 37. Basic parts of a thyristor are, so when we have a thyristor, you have 4 layers of alternate. So here we come 4 layers with gates open. A silicon control rectifier can be on by making the supply voltage equals to the forward breakdown voltage. This is going to be false, right? So take it here is going to be false. Yeah, when with increase in the current of what silicon control rectifier. So if you are increasing the current, it's not true or false. Okay, here with a gate open. Okay. Okay. So that one, like I said, false. We are moving to 39 rather, question 39. With increase in the gate current of silicon control rectifier, the forward breakdown voltage will, so this voltage will then decrease, right? It will decrease to a much lower voltage. So we have D. We know that when you increase the gate voltage, so the voltage will now reduce to a much lower voltage. So 40, question 40. A silicon control rectifier has 3 terminals, namely, we have the anode, cathode, and gate. So this is A. Silicon control rectifier is made of silicon and not germanium because it is what? Cheap, right? Meaning it is inexpensive. The holding current in a thyristor is less than the latching current. It's less, okay? Less than the latching current. How many modes of operation occur in thyristor? We have 3. We have the reverse blocking mode, the forward blocking mode, and then forward conduction mode. Question 44. With silicon control, when silicon control rectifier is off, the current in the circuit is, so the current here has to be lower than the holding current value. So it's not necessarily 0. So I mean you have some small current. So we have some small leakage current. So the answer here, C. If the firing angle in silicon control rectifier circuit is increased. Here, what do you mean? The fire angle here is a triggering angle. We know that if I have the maximum kind of conduction for silicon control rectifier is 180 degrees, right? So if you are increasing that firing angle, when that triggering angle, you are increasing, you can see that you are reducing the conduction. So the answer here, the output then tend to what? Decrease. Now, question 4 says the angle of conduction in silicon control rectifier circuit can be changed by, so the angle can be changed by the gate, right? You are using triggering the gate. So it's B. With a silicon control rectifier, when a silicon control rectifier is turned on, the voltage across it is, when you turn it on, the voltage across is not necessarily 0, right? So it's like 1 volt. When the thyristor is in the forward conduction region, it is regarded to be in the conduction mode. When you are in the forward conduction region, you are in the conduction mode. Question 49. A silicon control rectifier is turned off by reducing the voltage to the anode voltage, right? You reduce the anode voltage to 0. Question 50. The normal way of turning on silicon control rectifier is by you want to turn it on appropriate anode current, appropriate gate current. So here meaning you add the what to the gate. You want to turn on listen. So meaning it has to do the current that you are going to add to the gate. So this becomes B. So we've come to the end of this part of the solution. So we continue on the next video. Bye bye.